In this video, I'd like to get the equations of motion, the differential equations of motion for describing a mass that's attached to a spring in a non-dissipative system. So our model that we're going to look at, right, is basically a basic spring attached to a mass m, and again, it's going to be frictionless. So it's non-dissipative. I'm going to assume that the spring has the spring constant k. It's at equilibrium. I'm going to displace it by a certain amount and let it go, and so it'll start oscillating. And I'd like to know exactly the equations of motion. The equations of motion are differential equations or integral equations, but Newtonian mechanics we're all going to be using differential equations. Find the differential equations of motion, or the equations of motion. So find the equations of motion of the system. So let me start off by assuming we know that the sum of all forces, so free body diagram, so we could do a free body diagram, but I think it's okay. The free body diagram, there's only one force acting on it, so this is mass times acceleration, which is second derivative of x dt squared. And we're assuming x is positive going to the right hand side, and that's equal to minus kx, where k is the spring constant associated with b. So this is our differential equation. So this is the equations of motion that we need. So if you're given a mass m with a spring constant k associated with the spring, and we get a differential equation, and I'll change this differential equation around slightly into a more standard form that I'd like to go over, and this will be x is equal to 0, where k over m is a positive integer. And to signify this, right, in my lecture notes I'll be using, and in my course notes, I'll be using k over m, and for a not so obvious reason I'm going to call this as omega squared. Later I'll call this as angular frequency, but just for now, angular frequency. Just for now, just know that, so we have a second order differential equation, so we need two basis vectors for solving it, and to find the general solution, I'm going to basically call this as omega squared, so that whenever we see an equation that has a positive number, I'll always write this in terms of omega squared, so we can generalize the differential equation. There'll be a lot of equations where we look at systems with small vibrations, and we'll be able to use the same constant to get the angular frequency. But for now, this is the equations of motion. So here is the equations of motion for the system. It's non-dissipative, and later we'll actually see that non-dissipative systems, right, can be easier done by looking at Lagrange equations of motion. But for now, we're actually using Newton's equations of motion, and then we're going to augment Newton's equations of motion with dissipation, because you can't do that in Lagrange equations of motion. But anyway, so here's our equations of motion. I'm going to rewrite this in terms of omega O squared, and for now, it's not so obvious exactly why. Sorry, I kind of lost my... So just to remind you, I'll write this in the top left-hand corner so that we know that the ratio of k over m is going to be written as omega squared. So the spring constant to the mass is omega squared. And I'm going to solve this second order differential equation. So our equations of motion in our new rewrite is written as omega O squared over x is equal to 0. So we know that this is a second order differential equation. We're going to do a substitution of x is equal to E. Since I can't use k, I'll actually use ut. So when we substitute this for our differential equation, we get a characteristic equation that looks like u squared plus omega o squared equals 0. So remember, the general procedure for solving homogeneous linear differential equations. So we get a characteristic equation of u squared plus omega o squared. So we can solve for u, and moving everything to one side, you'll see that u is equal to plus or minus, actually, u is a member of the set I omega o minus I omega o. So automatically we should know that the basis vectors, right, for this differential equation is given by our basis set is given by e omega o t, because we're using t as the independent variable, e to the minus I omega o t. Now, so we know the general solution, right, is going to be equal to x is equal to c1 e I omega o t plus c2 e minus I omega o t. The problem is that c1 and c2 are both complex numbers, and we want to work in real values. So instead of using this basis, we know that any basis functions that are conjugate pairs, we can replace them with sines and cosines. And so our new basis is going to be equal to the sine of omega o t and cosine of omega t. So this means that our general solution for the second order differential equation, whenever we see it, we have to make sure that we get omega squared, that the general solution is going to be some constant, let's call this C3, times the sine of omega ot plus c to the 4 cosine of omega ot. And of course, we can always convert these sines to cosine in terms of some kind of an amplitude times omega ot plus some kind of a phase angle. So this is what I'm going to do. So I'm going to say that instead of writing sines and cosines separately, I'll write a single sine or a cosine with omega t plus a phase angle and an amplitude a, where the amplitude is nothing more than c3 squared plus c4 squared square root. So Pythagoras Theorem. So the phase angle we can calculate based on the values of c1 and c4 and what quadrant it falls into. We can get the phase angle. But that's not really important. The main idea that I want to get across is that the general solution is going to be written as this. Once we have this general solution, right, of this second order differential equation with no dissipation, there's no dissipation in the system, we can now ask ourselves, what does this really mean? So what is omega O? And I know this sine function means that it is some kind of a system that's periodic. So it's got a sine and a phase angle, so I should be not in the origin, so maybe it's slightly off, so it might be something like this. So the amplitude is given by A, and there's a phase shift in this sine function, which I'm not going to bother explaining. But so the main thing I want to get across is that we have a function that has an amplitude and is periodic. And what period? So we should ask ourselves, when does this function repeat itself? So here's x at t, and I know that it's periodic, so if I take some value of t, here's t, I know sometime later, this value, some time period later, it's periodic, the function repeats itself. So I'm expecting x at t plus t. So we can plug it into the original equation, so we can say that this is a sine of omega t is equal to a, oops, I got the phase angle wrong, so I'll put that in, is equal to a sine of omega t plus the time period plus phi. So these two functions must be equal to each other, and I can expand this further. And what you should see is that I don't know what time period is, but I know that if I look at omega ot plus phi and omega t plus phi, these functions must be identical for all values of t. For any t, I shift and I get the same function again. So we ask ourselves, what is the smallest value that is not 0 that will cause the shift? And the idea is that omega ot generally has to be a period of 2 pi, because we know sine and cosine functions, right, have a period of 2 pi. So we're expecting 2 pi n. But the smallest value of n, right, that's not 0, right? Otherwise we'll have the same functions, right? So the smallest value of n would be plus or minus 1. And if I use plus or minus 1, I can rewrite this and say that the magnitude of omega times t is equal to 2 pi times 1. Notice I did an absolute because this could be plus or minus 1. So this means that the time period of this oscillatory system, right, is 2 pi over omega O. And if I switch this around, and it's an absolute sign, I can write this and say the magnitude of the angular frequency is 2 pi over t. And this is why I call this angular frequency. So if you have a system that's period of t, we know that its angular frequency is 2 pi degrees. So if you have a system like a circle, an object going around in a circle, it does 2 pi radians in a time period t. So if you have an object uniformly traveling in a circle, we're expecting that 2 pi over t is the angular frequency. And that's the reason I called this omega as angular frequency earlier. So it was because I knew a priori that this was angular frequency. But the main idea you should get through this, right, is that whenever we see this differential equation, we will always write a sine omega ot plus phi, and the time period is just 2 pi over the absolute magnitude of omega O. And so specifically we can plug it into our original differential equation where we looked at, so let me erase all the unnecessary stuff. So our system originally, right, had the spring system consisting of a spring attached to a mass of k over m, and we said that omega squared is equal to k over m. So we can substitute it in, and so we have that the time period is equal to 2 pi over omega O magnitude, but omega O is equal to the square root of k over m. Spring constant and the mass are already positive, so we don't have to worry about the positive sign over here. And so we're left with 2 pi square root of m over k. So given a simple system, right, of a mass attached to a spring with a spring constant k, we're expecting that if I pull that object, the mass, lightly on a frictional surface, I'm assuming frictional surface, this thing will oscillate. And the time period of this oscillation is given by this equation that says t is equal to mass over the spring constant, square root of the mass over the spring constant.